Welcome everyone to Chapter 6. In Chapter 6, we're going to primarily be looking at normal probability distributions. We're kind of going to be under the umbrella of continuous probability distributions, and we're going to spend probably 5 minutes talking about uniform probability distributions, which are also a type of continuous probability distributions. But the whole remainder of the chapter, we're going to be talking specifically about the normal probability distributions. Okay, so one thing I want to say before we get started is there are more than one way to find normal probability values. MyStatLab may refer you to tables, and I would say we're not going to be using the tables. Tables are kind of old school, and we just don't use them that much anymore. Our calculators very easily find these probabilities for us, so don't let MyStatLab confuse you when they're trying to send you to a table. I just want you to use your calculator to get those values. Okay, so the first section we're going to look at is going to deal with standard normal distributions. Okay, so to start, I want to talk about uniform distributions. So uniform distributions are a type of continuous random variable. So in the last chapter, we talked about discrete random variables. So with discrete random variables, we could list our outcomes. With continuous random variables, we're unable to list our outcomes. So here, we're going to represent it graphically because with discrete, it was either 0 or it was 1 or it was 2 or it was 3 or 4 and so forth. With these, it could be 0.5, 0.59, 0.6389743. I mean, it doesn't really matter. There's infinitely many possible values, and so that's why we represent it with a graph instead of a table. So, like I said, we're going to look at uniform distributions, and in these, the values are spread evenly over the range of possibilities. So this one shows from 0 to 5. Happens to be the example I'm using. It could have gone on further or it could have stopped shorter than that. But it's spread evenly over a range of values, and it's going to be represented by a rectangular shape because it's the fact that it's spread evenly indicates that this is going to be a flat line here across. Okay, some of the properties for uniform distributions, the area under the graph of a continuous probability distribution is always equal to 1. That's true for uniform distributions and for normal distributions. So this total area enclosed by the rectangle is always going to be 1 on our problems. Okay, and this is a super important concept here, and that is that there is a correspondence between area and probability. So if you're asked to find area, you're basically finding probability. If you're asked to find probability, you're essentially finding area because they're going to be one and the same as we go through this chapter here. Okay, just a note, because we are working with rectangles, we can find the area, which is therefore the probability, by simply doing width times height, length times base, whatever you're used to, but basically multiplying our two sides together. Okay, so all density curves have certain characteristics. So what you've been seeing there with the uniform distribution is a density curve, and this is another example of the density curve. This would be for the normal distribution. This would be a density curve for the uniform distribution. But for any density curve, the graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. So this total area is 1 and this total area is 1. So it's not really dependent upon the shape. The area itself is going to stay 1. Okay, there on MyStatLab, when you have some questions, you're going to have to actually figure out what your probability is. So I wanted to show you an example here. This one, you've got the waiting times between a subway departure schedule and the arrival of a passenger are uniformly distributed between 0 and 9 minutes. So on our problem here, if we look at this, and you'll have to forgive me for not being able to draw nice straight lines, but basically it's uniformly distributed between 0 and 9. Okay, so a uniformly distributed tells me it's going to be rectangular in shape. And I also know that this area in here is going to be 1. So what I have to do is I have to find the probability. I have to find the height of this rectangle, basically. So if I know the area equals length times width, or base times height, or whatever you want to use here. Then my length here, if I'm letting this be my length, this is 9 units. So that's going to be 9. I know my total area is 1, and so I can use that to find the width. So my width is going to be 1/9, or you could convert that to a decimal. So this value here is going to be 1/9. Okay, so here's one. During certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 5 minutes. So we've got 0 to 5 here. So all the values are equally likely. So if we need to figure out what this probability is, we're going to go back to the area equals length times width. We know our area is 1, and we know that this dimension here is 5. And so we can find our other dimension here by just by leaving the W in. So we'll divide by 5. So W would be 1/5 or 0.2. Okay, so all of these different values in here are equally likely. So 1 is just as likely as 1.5, 2.1, 3.68. All of those are equally likely. So we want to look at a couple problems here. Given the uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. So at least 2 minutes is going to be greater than or equal to 2. So what I'm going to do is I'm going to come down and I'm going to look at shading this greater than or equal to 2. So this is the part that I'm looking at. This is my greater than or equal to 2. So basically what I have to do is I have to find the area of this shaded rectangle. Do an area as length times width. Okay. So looking at this rectangle here, my width, or whichever way you want to call it, this dimension here is going to be 3. And the vertical dimension on it is 0.2. So from here, my area is going to be 3 times 0.2. Or 0.6. It makes sense that this would be less than 1 because we know that the total area is 1, and this is actually 3/5 of the total, so 3/5 of that's going to be 0.6. Okay, so here's another one. Given the uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a waiting time of between 1 and 4 minutes. Okay, so we're going to go and look at from 1 to 4, and again, forgive me for not being able to draw my straight lines. So this is the area that we're looking at this time. So again, I need to figure out the area of that shaded region. So it turns out this one's actually going to have the same probability because the width of it would be 3, the height would be 2, so it ends up with a probability of 0.6. So you can mark this off in any different way to describe this. As far as the probability notation, we're going to look at the probability that x is between 1 and 4. One thing I wanted to say is that it really doesn't matter whether my inequality looks like this or like this. And I know that's a little bit strange because we know that in pure math classes, it does make a difference. But with these continuous probability distributions, it really doesn't make a difference because we talked about that there's infinitely many values along this line. Each one individually has such a small probability associated with it that it doesn't matter whether we include or don't include these particular values when we calculate it. So don't be not like when we did the binomial distribution, we really had to focus on whether those values were included or not. For the continuous probability distributions, we do not have to worry about that. So that makes it a lot nicer. Okay, here's one for you to practice on. So pause this and try these. Okay, the first one here, find the probability that a randomly selected voltage level is greater than 124.5. So this was, I don't think it said, but this is actually referencing voltage levels. So they were uniformly distributed between 123 and 125. So when you look at this here, that's if we find the height to get this 0.5, what you're going to do is this one has a width of 2 because that's 2 units in here. So this value is going to be 1/2, which we know is 0.5. So that's how we get this value here. And then if we look at greater than 124.5, that's this shaded region. So my area for that shaded region is going to be 1/2 times another 1/2, or 1/4, which is 0.25. Okay, here we're looking at between 123.5 and 124.5. So if I'm going to find the area of this shaded region here, its width is 1 unit because each of these marks is a 1/2 a unit, so 1 unit, and the height is 0.5. So that's where I get this 0.50. Okay, moving on to the standard normal distribution, which is what we will talk about from now through the end of chapter 6, and then actually on from there at times. So some characteristics of standard normal distribution. Our distribution is bell-shaped. So the graph of standard normal is bell-shaped, is symmetrical. We've talked about it before. It looks something like this as far as the shape of it. The mean of standard normal is 0, and the standard deviation is 1. So these are values that you need to know because you need to know the characteristics of standard normal distributions. So it's very important. The reality is not a lot of distributions have a mean of 0 and a standard deviation of 1, and we'll talk about how to deal with those in chapter 2, section 2. But for now, it's really important to understand the foundations of what standard normal looks like. Okay, so like we said, it's symmetrical, and the area, it is a density curve, so the area under this curve is still 1. It has a mean here in the middle of 0, and the standard deviation is 1. We will not work with this equation. This is actually the equation, if you were to put it in your calculator, that would draw the normal curve for you. You would need to know what the mean is and what your standard deviation is, which of course we just talked about. For standard normal, the mean is 0 and the standard deviation is 1. But that would be what would give you this graph. This is not a function-based course, it's statistics, and so we're more concerned with these probability values associated with it than actually being able to sketch the curve itself. Okay, keep track of your z-scores and your area. It's easy to get a lot of confusion between these. Z-scores will always go along your x-axis, and area or probability is always going to be interior to the graph itself. It's going to be the region under the curve. Okay, I want to show you how to access this on your calculator. As I mentioned at the very beginning, we're not going to use tables. We're going to use our calculator to do that. So here's some information on this, and I'm going to switch over to the calculator so that I can show you all this on the calculator. Okay, so you're going to go to second and vars, and that's going to bring up this distribution menu. You're going to go actually, you're going to go to number 2 here because we're talking about the normal distribution. You will not use this first one at all. So with binomials, we had to decide, was it a PDF or a CDF? We don't have to do that for normals. We're only going to be using number 2, and then we're going to come back and look at number 3 a little bit later, but you are not going to be using number 1 at all. Okay, so it either brings this up or you're expected to enter these different values here. So you're going to have to enter either a lower bound, an upper bound, your mean, and your standard deviation. It should be preset to 0 and 1 for the standard normal. And as far as like, there will be occasions where we have to put in infinity. So the way that we're going to enter infinity is if you see this little double E over the comma, we're going to, and I'm just going to kind of show you here how we would enter that. We're going to go second comma, and that brings up the E, and then we're going to type in 99. What that is 1 times 10 to the 99th power, which is just a super large number. And so that's how we're going to enter infinity in. And this is how we would enter negative infinity in when it comes time to do that. So just keep that in mind as far as how to get to that E. The E is right above the comma when we start entering these in the calculator. Okay, we're always going to give our probabilities to 4 decimal places, and our z-scores will actually give to 2 decimal places, which I'll talk about in a few minutes. Okay, so I'm going to look at 3 different cases. The first case is where I'm actually finding the probability between 2 different values here. So I have something, and I'm going to sketch down here. Always start with these thumbnail sketches. It's super important that you sketch out what you're talking about. So let's say that and this should actually be a Z, it's a typo. So if I'm doing a standard normal distribution, I've got 0 here in the middle. So I'm going to be at negative 1.3, and I'm going to be over here at 1.5. So I'm looking for this one for the part in between these two. So if I'm looking for the part in between these two, what I'm going to do is I'm going to go where I just showed you on the calculator, and I'm going to do the normal CDF. So choose normal CDF. So then it'll bring up a screen that looks like this. You're going to enter your lower bound, which is this one, and you're going to enter your upper, which is this. You're going to set your mean at 0 and your standard deviation at 1, and then press paste and enter. When you do that, it's going to bring up something that looks like this. So if you don't have these prompts that come up on your calculator, the first thing that you need to enter is your lower bound, then you need to enter your upper, and then your mean and your standard deviation, and put commas in between each one of them. So depending on the version of the calculator you're working with, you may see this screen, or you may just have to type it in like this. When you press enter, depending again on your calculator, you're going to get this value here. That is your area, and that's also your probability that you're trying to find. That's the probability that on a standard normal curve is between z, if the probability that z is between negative 1.3 and positive 1.5 is going to be given here. So we'll round that to 4 decimal places, and that would be our answer. Okay, other times we have cases where we have one of the tails of the graph. So on this one, I'm looking at a situation where I have my z-score is over here at 1.3. So I'm going to look at greater than 1.3. Okay, so this is a right tail that I'm looking at. So if I have a right tail situation, and I've got to come up with my lower and my upper bounds. My lower bound is going to be the 1.3, and since this goes off into the tail of the graph, it's going off to infinity, which is going to be my upper bound. So when I enter it in the calculator, the lower bound will be 1.3, and my upper bound is going to be that E99 that we talked about. So, and again, if I need to enter it this way, I can. So press enter, and you'll get this as your value. It may not be bringing up this graph for you, and if it doesn't, that's fine as long as you're able to get this value here. Okay, the third case is the left tail. So let's say we're looking at the normal distribution is standard normal, so we have a mean of 0. Here for our example, we're going to look at less than negative 1.25. So here's my negative 1.25, and it's less than that, so it's going to be shaded in this direction here. Okay, so always read the graph from left to right. So because if I'm reading it from left to right, negative infinity is going to be my lower bound, and negative 1.25 is going to be my upper bound. So I'm going to put in negative E99 for my lower, negative 1.25 for my upper, 0 and 1, and I'm going to get this as my value here. And you can see that's the same as down here. Okay, I have some for you to practice with. On each one of these, I want you to do a little sketch where you shade in the region that you're talking about and then identify the probability. I would suggest, especially as we're getting started here, for you to write out what you're entering for your lower, your upper, your mean, and your standard deviation. That'll help you to stay organized. And it'll also help me when I'm looking at your work on a test to know what you entered in your calculator. Otherwise, I really don't know what you do wrong with that. So try these and then check your answers. Okay, on the first one here, we've got z greater than 1.27. So start out with your standard normal curve and sketch in greater than 1.27. So this is a right tail. So our lower bound would be 1.27, and our upper is going to be the E99 to 0 and 1, and then round it to 4 decimal places. This is 4 decimal places and not 4 significant digits. So there is a difference there. So we'll do 4 decimal places here. Okay, the next one is one where you have the lower bound and the upper bound provided. So you'll do the normal CDF from negative 1.3 to positive 1.3, and you can see that you get this probability. One note, if you're ever coming up with a negative probability, then it's wrong because probabilities are never negative. One thing that can cause that is to have reversed your upper and lower bounds. So check and make sure you have them in the right order if you're getting a negative probability. Okay, here we have the probability that z is greater than or equal to 1.6. Remember I said the equals part isn't going to affect how we set this problem up. So we're still going to do a normal CDF. It's a right tail, so it's going off to positive infinity. So we're going to put the E99 in the place of the infinity. So 1.6 to infinity, 0 and 1 gives us this for the probability. Here I'm looking between 0 and 1.96, so I'm going to mark off 0 and 1.96, shade that in. So this will be my lower and my upper, and I get this for my answer. Okay, this one is another one where I have my lower and my upper bound provided. So it's going to be this region. So I'll do the normal CDF from these two values, 0 and 1, and I get this as my answer. This one is going to be a right tail, so we'll sketch in the right tail of the graph. I'll do from 0.82 to infinity. So that would be the E99, 0 and 1, and I get 0.2061 for my answer there. This one is a less than, so it's a left tail. So I'm looking at this tail here. So reading it from left to right, I'm going to do negative infinity as my lower bound, and this as my upper bound. So when I do this, I'll put negative E99 in for this, and I get this as my answer. The next one is less than 1.59. So even though 1.59 is way over here, I still, because this is a less than, I shade all of this in. So I'll do from negative infinity. So starting at the left, this will be my lower bound and my upper bound. So lower bound will be negative E99 and then positive 1.59 for my upper bound. Okay, we're looking between these two values. So I'm going to do normal CDF between this is my lower and my upper. And greater than negative 1.96 is going to be all this whole thing. So it would be from negative 1.96 to infinity. So I'll put in the E99 there. Okay, that takes us to another example here. This one deals with bone density test. A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a Z-score. The population of Z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these results meet the requirements of a standard normal distribution. So if they didn't tell us that, just the fact that we have a mean of 0 and a standard deviation of 1, that allows us to go ahead and treat this as standard normal, and we'll get into non-standard in the next section. So here are 3 for you to try. I would like for you to read through them, try to set these up, and then check your answers with them. Okay, the first one here, a randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score that's less than 1.27. So if we sketch in the, always do the sketch. It's hard to visualize it without doing that. So sketch it, put the 1.27, and we're trying to find back this way. So this is going to be a normal CDF. Our left bound is over here at negative infinity, so negative E99 to 1.27, 0 and 1 for standard normal, and that's going to give us our answer. So our answer should be 0.8980, and basically we interpret that to say that 89.80% of the people have bone density levels below 1.27, because all I'm doing is moving my decimal place 2 places to the right in order to get that to a percentage. Okay, here's another one. Using the same bone density test, find the probability that a randomly selected person has a result above -1. Okay, so if we look at this, we've got our mean in the middle. Always put your mean here. Here's -1, and we want to find the probability that it has a result above that. So we're looking for the probability that our z-score is greater than -1. So that's going to be shading this region here. So going all the way off to infinity. So I'll have a normal CDF from -1 to infinity, which we put in as E -99. And so my answer on that one is going to be 0.8413. So about 84.13% of the people have bone density levels above -1. Okay, the last one of this example here, we're looking at a bone density reading between -1 and -2.5. Okay, so we start out with the mean in the middle here. Here we'll say is -1, -2.5. So we're looking to find this probability here. So we'll do the normal CDF from -2.5 to -1. And that's going to give me this probability here. So that value is 0.1525, or about 15.25% of the people have bone density readings between these two values. And so this is just some notation. So if it's between A and B, then this would be the notation. If it's greater than A here, and if it's less than A, this would be the notation. Okay, so we're going to turn things around at this point. We've been taking a z-score and finding the probability that corresponds with that. Here we're going to start with the probability, and we're going to find the z-score. We're going to work completely in the opposite direction. So I'm going to kind of show you an orientation to this on your calculator, but before we get to that, a couple things. Always draw and label the area that you're talking about on your curve. And a lot of the calculators, you're going to have to enter the area to the left. So if it doesn't give you the option of choosing left, right, or center, then you have to always enter the area to the left. So whatever this area to the left is, that's the part you're going to have to find. And that's kind of how I'm going to structure the lesson, just because that's going to apply to everybody can do it as the area to the left. If you have like a newer calculator and it gives you other options, then you can use those if you choose to. But that's not how I'm going to tailor the instructions. So we're going to be using the function inverse norm to do these type problems. So on your calculator, so here on your calculator, to get to the inverse norm, you're going to go to second and vars. It's going to be number 3. So if we put in number 3. Okay, there's a couple things. If it's asking for the area, then it's asking for the area to the left. So let's say the area to the left is 0.75, and then we put in the mean and the standard deviation and press enter. It's going to write it like this. So if you have one that doesn't give you prompts, that's what you're going to do. You're going to enter the area to the left and then the mean and the standard deviation and press enter. Some of you have the choice of choosing right, left, or center, and if you understand how to use that, then that's fine to do that. Okay, so last thing, your z-scores are always going to be given to 2 decimal places. There's 2 exceptions to that we will encounter. I'll tell you when we get to those, but otherwise round it to 2 decimal places. Okay, so the first one here is, okay, the first one, you're given a diagram here or a graph of the normal distribution, and we have this value labeled for us. We're asked to find what the z-score is. So we need the z-score that cuts our graph in such a way that 0.9671 is the area to the left of that. It's also the probability associated with this z-score here. So what we're going to do is we're going to do inverse norm. This is going to be the area to the left of my z-score. So whatever my z-score is here, I'm going to give the area to the left of that, and then I'm going to put in my mean and my standard deviation. So I'll enter that, and that'll give me 1.84, and that's going to be my answer. Okay, here's one that's a little bit more complicated. Each one of these has a little twist to it. So if I look at this one here, I need to have the area to the left of this z-score in order to use my calculator, unless you happen to be one of those that gives you the choice of choosing the area to the right. If you have that and you can choose area to the right, then put in area to the right and enter this value. Otherwise, we've got to figure this area to the left. So that's going to be 1 minus 0.038. So I'm going to have 0.9619. Okay, so from here, once I have the area to the left, my z value or my z-score is going to be the inverse norm of 0.9619, 0, and 1. So that value is going to be 1.77. All right, here's another one for you to try if you feel comfortable and want to give this one a try. Try it, and then see how you should do this one. Okay, on this one you were given 0.4175 is the area here between 0 and the z-score. So if I'm going to use this, if I'm trying to find this value, then I need to find the area to the left of that in order to get my calculator to correctly identify it. So we know that the whole area here is 1. We also know that half of it is 0.5. And this half over here is also 0.5. So if I do 0.5 minus this part, it's going to give me this part here that I'm trying to work with. So this part here is 0.0825. So I'll do the inverse norm of 0.0825 with the mean and standard deviation, and I get this as my z-score. And it makes sense that this will be a negative z-score because it is to the left of my mean, and that's what I would expect to have. Okay, here's another example. Again, try this one. See if you can find this z-score here. Okay, on this one, we know that half of the graph is 0.5. So if this is the z-score that I'm trying to find, I need to find the total area to the left of this. So I'll have to add these two together, and that gives me this 0.9066 when they're added together. 0 and 1 for standard deviation and mean, and I get 1.32 for my z-score. Okay, here's a few other examples. If thermometers are used with temperature readings at the freezing point of water that are normally distributed with a mean of 0 and a standard deviation of 1, find the temperature corresponding to the 95th percentile. It's very important that you know how to transfer these percentiles onto your graph. So this one we have a mean of 1 and a standard deviation, sorry, a mean of 0 and a standard deviation of 1. So that tells me I am working with standard normal. Okay, so here's my mean of 0. I'm looking to find the 95th percentile. So if you recall when we talked about percentiles, the 95th percentile is the value such that 95% of the values are below that. So I'm going to come over here And I'm going to represent this. And so 95% of the values are below this line that I drew. So this area in here is going to be 0.95. And this is the z-score that I'm trying to find, such that 95% are below that. So I'll do the inverse norm of 0.95, 0, and 1. And I get 1.645. And this is one of those that we are going to give to 3 decimal places. This one occurs very often. So when you see this 1.64485, we're going to round that to 1.645. Okay, here's another one. I'm using the same thermometer that we had described before, which had a mean of 0 and a standard deviation of 1. We want to find the temperatures, so we're finding 2 here, that separate the bottom 2.5% and the top 2.5%. So I'm going to go and I'm going to draw 2 lines, one that cuts off the bottom and one that cuts off the top. So this is going to be 0.025 because that's going to represent the bottom 2.5%. This is going to be 0.025. Okay. We know the whole thing is 1, so if I take away the 5% that's combined between these two, I'm going to get 0.95 for my middle part here. So I've got to find this z-score and I've got to find this z-score. I've got 2 to find. The first one, I'm going to do inverse norm. The area to the left of this is this 0.025 with a mean of 0 and a standard deviation of 1. So I get negative 1.96. For the second one, which is over here, I'm going to do the inverse norm. I'll combine these two together because I have to have the combined area to the left. So I need this part and I need to add to it this part here. So I'm going to add both of those together and get 0.975. So I have 1.96. And it makes sense that these are the negative of each other because they're centered here at 0 and it's a symmetrical graph with this centered at 0. Okay, here's another, we want to find the 90th percentile for the bone density scores. So if you remember, the bone density scores were standard normal. So if we're looking for the 90th percentile, I'm going to draw a line that separates the 90th percentile or the lower 90 values from the upper 10% of the values. Okay, so if I'm going to find this, I'm going to do inverse norm 0.90, 0, and 1, and I get 1.28. Okay, sometimes you'll be asked to find the critical value, and a critical value is a z-score on the borderline that separates those z-scores that are significantly low or significantly high. Okay, so when you have notation like this, then this alpha here that they're giving you is going to represent the area to its right. So if I have to find z of 0.05, then what I'm going to do is I'm going to find the z such that 0.05 is to the right of it. So that's what this little subscripted notation means. So for one like this, we're going to find the area to the, we're going to find the z-score that has the 0.025 to its right. So that's going to look like this. So if we have 0.025 to its right, then I'll do 1 minus 0.025 and I'll get 0.975. So that's the area to the left. And remember, that's what our calculator always expects unless you have one of the newer calculators. So this is going to be the area to the left and then the mean and standard deviation. Okay, this is one of the homework problems that I tend to have people ask a lot of questions about, so I wanted to address this. So on this one, you want to find, it says about blank percent of the area is between -1 and 1. So I want you to think about if it's standard normal, then we're going to look at from -1 to 1. So we're going to do the normal CDF from -1 to 1. and we're going to get that probability. So anytime you're asked to find percents or probability, you are going to do your normal CDF. If you're asked to find percentiles or any other score, those are you're going to be doing your inverse norm. Okay, so this value on the calculator is 0.6827 if we round it to 4 decimal places. So this would be about 68.27%. If you recall, by the empirical rule in chapter 3, we expect within one standard deviation to have roughly 68%. So if we were to do a formal calculation, it's actually 68.27%. But that's how what we would find there. So for bone density scores that are normally distributed with a mean of 0 and a standard deviation of 1, find the percentage of scores that are significantly high. So to be significantly high, we need to be at least 2 standard deviations above the mean. So what that's going to mean is 2 standard deviations is going to be represented by a z-score of 2. So if you're at least 2 standard deviations above the mean, you're going to be finding this part of the graph. So we would have a normal CDF from 2 to infinity to answer part A. Part B, significantly low. So significantly low is going to be over here and be less than -2. So we're going to do the normal CDF from -infinity to -2, and that would give us part B. And then part C, the part that is not significant, that's this part in the middle here. So we'll do the normal CDF from -2 to +2, and that's going to give me those that are not significant. Okay, here's a couple for you to practice with. Decide whether you'll do the normal CDF or the inverse norm, and then try to answer these. Okay, on the first one, you're finding a probability. So because I'm finding a probability, I'll do a normal CDF, and it would be a right tail. So it's going to be 1.6 to infinity, and we get this answer. The second one, you're given the probability, you're asked to find a z-score. So I'm going to do the inverse norm, and this time I need the area to the left of this line here. But I was given the area to the right, so I have to do 1 minus that area that they gave me in order to get the area that I'm going to use. So this is going to have to go here as the area to the left, then 0 and 1, and I get my z-score that's given to me here. So I did want to take a minute to show you how you can do this normal CDF type problems and inverse norm problems using StatCrunch. So if you're in StatCrunch and you go to Stat and Calculators and go down to Normal, it's going to bring up a screen that looks like this. So what I can do is, right now we're just talking about standard normal, so I'm going to have 0 and 1 for my standard deviation. Let's say that I have a problem x is less than 1.25, okay, and compute. So it sketches this in for me and it gives me that probability. If I want to change it to a right tail, then I would do greater than, and maybe I'm going to do greater than 0.79 and compute, and then it's going to give me that probability. If I want the part between two values, then I click between. This is showing the probability between -1 and 1. If I want to change that to between -2 and 2, and compute, then there's that probability there as well. So you can see you can play around with this. It doesn't really have an inverse norm type function. What you have to do with that is, let's say that I know that this probability here needs to be 0.83. Okay. Then I'll compute and it'll give me the, this is going to be the value that I'm looking for here, such that this area is 0.83. So you can enter any of these and it'll kind of work backwards from it if it needs to. So if I'm looking at greater than, and let's say that that I want the left tail to be not one, to be 0.75. Okay, so this score here, which is 0.67, if I look at the probability that x is less than that, that's going to be 0.75. And between, it's a little bit tricky there, but if you know that you want the probability between two symmetrical values to be 0.3 and compute, then it tells you kind of the scores such that that would be the probability. So if you're interested, you can play around with that a little bit and kind of get familiar with it. And we will have a StatCrunch lab for this chapter, so you will need to come back to this at that point for some instruction on it. Section is very fundamental to what we're going to be doing for the remainder of the course. So if you have any questions, please get those questions answered and don't let them linger because you're going to get further behind. So I hope everyone has a wonderful day, and I'll see you next time.